Today we're going to start talking about Chapter 20, which is all about nuclear chemistry and radioactivity. Today what we'll discuss are the different types of nuclear reactions. There are 5 of them, and each of those nuclear reactions we're going to see cause a change in the nuclei, which is going to be associated with a change in the identity of the substance. And then we'll look at how we can predict nuclear reactions based on this band of stability or valley of stability. So nuclear can be quite controversial. In a lot of ways, nuclear is awesome because there's so much energy stored in mass. And if you can harness that energy, it could really help solve the energy crisis. But nuclear can be difficult to control. If you've heard of Chernobyl, you have an idea of what can happen when things aren't controlled. So I'd like to start by just looking at this TED-Ed talk.
On a December afternoon in Chicago during the middle of World War II, scientists cracked open the nucleus at the center of the uranium atom and turned nuclear mass into energy over and over again. They did this by creating for the first time a chain reaction inside a new engineering marvel, the nuclear reactor. Since then, the ability to mine great amounts of energy from uranium nuclei has led some to build nuclear power as a plentiful, utopian source of electricity.
So nuclear reactions are different than the type of reactions we've been looking at because they don't follow the conservation of mass. We see that some of the mass that in our reactants gets converted to energy. And that energy, like the video showed, can be used to heat up water and then generate electricity. What's balanced, though, is the number of particles that we observe. So the number of subatomic particles that we have on our reactant side must equal the sum of the subatomic particles on the product side. Because we'll have an equal number of particles and that those particles change, we're going to see that typically the element's identity is going to change also. Depending upon the type of decay that we observe, we'll see that those elements are either going to become they're either going to contain more protons, in which case they would move up the periodic table, or they're going to contain fewer protons, which would make them move down, have a lower atomic number. I don't explicitly write out any of the terminology used for nuclear reactions. Much of it comes from what we learned early on in 141 when we talked about atoms and isotopes. I'm going to use the term nuclide when I'm talking about a specific isotope. Those nuclides are going to have a specific number associated with them, and that's going to be our mass number, which will help us to identify the number of neutrons contained within the atom. So there are 5 different types of radioactive decay that we're going to observe. We're going to see that with each type of radioactive decay, we're either going to release particles like electrons or something called an alpha particle, which looks like a helium atom, or we're going to see that we release energy in the form of photons, which we're going to call gamma rays. Rutherford is responsible for discovering these 3 types of rays. Alpha particles, which alpha particles look like a helium nucleus. There are 4 mass units, 2 protons, and then the other 2 are neutrons. It has a +2 charge since there are no electrons. Beta particles are like electrons, so they're massless, but they have a charge of -1. And then gamma rays. Gamma rays, like I mentioned, are photons, so they're light energy, and they don't have charge or mass. We're also going to see that some of these isotopes can emit what we call a positron. A positron is like an electron, but instead of being negatively charged, it's going to be positively charged. So we'll use the same symbol for the positron, but our charge now is going to be +1. And then we can also see that in the 5th type of radioactive decay called electron capture, it's going to have a beta particle, but rather than that beta particle being emitted, that beta particle is going to be absorbed by the nucleus. So now let's look at examples of each one of these types of radioactive decays, starting with alpha decay. In alpha decay, we see the loss of an alpha particle, which again is like the helium nucleus. An example is radium-226 undergoing alpha decay. So we can see here our alpha particle. When that radium-226, which if you look at your periodic table, radium has an atomic number of 88. And then if we wanted to figure out the number of neutrons in this nuclide, we could subtract 88 from 226. When it undergoes alpha emission or alpha decay, we see that 4 of those protons and neutrons get lost. It's going to be 2 protons, 2 neutrons in that positively charged alpha particle. Those 2 protons that we've lost mean that we only have 86 total protons in the atom, which means that we're not going to have radium anymore, but instead we'll have radon, which is Rd. But again, in these nuclear reactions, we're always going to see that the sum of the subatomic particles on our reactant side is going to equal the sum of the subatomic particles on the product side for both products. So here we have 226. on our reactant side for the number of protons plus neutrons. Our alpha particle has 4 protons and neutrons, and then the radon 222 has 222 protons and neutrons. So we can see that the number of protons and neutrons is conserved on our reactant side to product side. We can also see this in the atomic number. So down here we have 88 protons in our radium-226, and on our product side we have 2 protons in the alpha particle plus 86 protons in radon-222 to give us a total of 88 protons on the product side and 88 protons on the reactant side. So now go ahead and try determining what reactant would be present in this decay here that results in the formation of niobium-240. And again, we're going to have conservation of our particles. So over here on the product side, we have 240 protons and neutrons, plus an additional 4 protons and neutrons from our alpha particle, which means that our reactant needs to have a total of 244 protons and neutrons. Down here, we have 93 protons plus 2, which means that we're going to have a total of 95 protons. So our answer has to be 244 over 95. And if we look up the symbol for the element with an atomic number of 95, we see that it's americium. So now let's look at beta decay, our next nuclear reaction. Beta decay occurs when an electron is emitted from the nucleus of an atom. And when that electron gets emitted, it converts a neutron into a proton. Which is strange to us, right? Because, wait, there are electrons in the nucleus. Well, yeah, you could say that a neutron is technically a proton and electron, positive energy, negative energy, and then we have our mass energy. So a neutron can be considered to be the sum of a proton and electron, creating a massive uncharged subatomic particle. So then what we see, like this example with uranium-239, is that when we release that electron from the nucleus, we get one of our protons to get converted to a neutron. So we'll have one of our neutrons converted to a proton, so we'll have one more proton in the nucleus, but the mass number, the sum of protons plus neutrons, is going to remain the same. So both alpha emission and beta emission we observe in natural elements that we find. And, however, there are other types of elements that we've made that can undergo new types of nuclear decay processes, specifically positron emission and electron capture. In positron emission, which is a lot like beta emission, we see the emission of a massless, positively charged subatomic particle. In electron capture, we see that instead of releasing an electron, we absorb an electron. And that absorbed electron will convert one of our protons into a neutron. So positron emission, like I said, is like beta emission, but we're releasing a positively charged subatomic particle. That positively charged positron can react with an electron, sort of canceling that electron. We're going to see that, again, we use the same type of symbolism for a positron, which you're going to see either beta, or you could also see an E. And the same is true for beta particles. You can either see this E with a -1, or you can see the beta -1 like we showed earlier. Again, a proton gets converted into a neutron as that positron is emitted. So that proton, which has a mass of 1 and a charge of +1, releases that +1 charge, so you end up with a neutral neutron with a mass of 1. So what we see is the mass number is going to remain the same because there's no mass that's released, but our atomic number is going to go down by 1 as we convert one of our protons to a neutron. An example is this polonium-207. This parent isotope can decay to create bismuth-207. Notice bismuth contains 1 fewer protons than our polonium because it's released this positron. Positron emission we use in a medical setting, specifically positron emission tomography. In positron emission tomography, patients are injected with a radioactive isotope that then travels through the body, and then that positron can undergo decay, and when it does that, we see that energy is emitted. So let's go ahead and just watch this quick video showing how PET scans work. And again, we would call those photons gamma rays. So like the video said, we get this 3D picture of tissue within our body, and then we detect the radiation or those positron particles through the gamma rays that are released when the positron interacts with an electron. Electron capture is our final type of nuclear reaction. In electron capture, we absorb, the nucleus absorbs one of those beta particles. And when that happens, we see that a proton gets converted to a neutron. So we still have this beta particle, but in electron capture, the beta particle is written as a reactor, as a reactant. If we were looking at electron emission, this beta particle would be on our product side. So now rather than having a neutron getting converted to a proton, we have a proton that gets converted to a neutron. So for example, here we have beryllium-7. That beryllium-7 can absorb a low-lying electron, and when it does that, we're going to see that the number of protons goes down by 1, and that proton gets converted to a neutron. So again, the mass number will remain the same, but the number of protons is going to go down. So now it's a chance to look at just a template reaction and tell me which type of decay occurs. The trick to this again is that you have to have conservation of your particles. So here our number of subatomic particles doesn't change on the top, which means that the particle that gets emitted is going to have zero mass. So we're not going to have alpha decay. Our number of protons, our atomic number, goes down by 1, which means that here we have to have 1 plus 1 for the charge of our subatomic particle that's emitted. So this then would be an example of positron emission. We would have 1 plus 19 gives us 20, 41 plus 0 gives us 41. Oftentimes, like the video showed that we started with, radioactive materials will get converted to other unstable radioactive materials. What we see is that oftentimes we have a series of decays that occur for a given isotope until we eventually reach a stable isotope. So here where we start with uranium-238, that uranium-238 can undergo alpha emission, giving us thorium-234, and then that thorium-234 can undergo a series of beta decays, eventually giving us uranium-234, which can then undergo a series of alpha decays to give us polonium-218, and again, et cetera, et cetera. In this case, the polonium can either undergo alpha decay or it can undergo beta decay. And then eventually what we end up with is a stable lead isotope, the lead-206 isotope. Our naturally occurring isotopes are only going to undergo alpha and beta decay. And then, like I mentioned, that will eventually give you an isotope that's not radioactive. What determines this is what we call the band of stability. So if we look at all of the isotopes, we see that stable isotopes exist in this yellow shaded region here. If we look at the ratio of our number of protons to our number of protons, which is our atomic number, for the smaller elements, we see that that ratio for stable molecules is roughly 1. However, as the molecules grow, as the number of protons and neutrons increases, that ratio also increases. So from about 20 to about 60, we can say that it's around 1.25, and then above 60, it's about 1.5. If we observe an isotope where the number of neutrons to our number of protons is too high, we're going to observe beta decay. And as a reminder, what happens in beta decay is a neutron gets converted to a proton by releasing an electron. So when this occurs, the number of neutrons is going to go down and our number of protons is going to go up, essentially reducing our N to Z ratio. When the N to Z ratio is too low, we observe either positron emission or electron capture. Sometimes we may also observe alpha decay, depending upon the isotope. For electron capture, remember that we have a proton that absorbs one of those low-lying electrons to generate a neutron. So in this case, our number of neutrons is going to go up, the number of protons is going to go down, effectively increasing our N to Z ratio. So let's look at 2 examples and then predict whether the nuclide, the parent nuclide, is going to undergo beta decay or positron emission. First, let's look at magnesium-22. Looking at the periodic table, we can see that this magnesium-22 isotope has an atomic number equal to 12. That means that the number of neutrons is going to be equal to 22 minus 12, which is going to be equal to 10. Our N to Z ratio then is going to be equal to 10 divided by 12, which is 0.83. So here our N to Z ratio is too low. We would expect, given the size of this atom, that it should have an N to Z ratio close to 1. In order for us to increase that N to Z ratio, we're going to observe electron capture. This magnesium-22, when it undergoes electron capture, it's going to create a sodium ion because the atomic number goes down by 1, so we would have an atomic number of 11 protons. The element that contains 11 protons is sodium, and then our mass number would still be 22. So our N to Z ratio then for this sodium-22 isotope is equal to 1. We have 11 protons and 11 neutrons. Now let's look at molybdenum-102. Molybdenum-102 has an atomic number of 42, which means that the number of neutrons is going to be 102 minus 42, giving us 60. Our N to Z ratio then is going to be equal to 60 over 42, which is equal to 1.37. That N to Z ratio is too high for what we would expect this sized atom to have. We want it closer to 1.25. So this means that we're going to observe beta decay. When we observe beta decay for this molybdenum-102, again, we'll see that one of the neutrons gets converted to a proton, giving us one additional proton. Our atomic number, again, when it goes up by 1, we change the element, but our mass number is going to stay the same. So now our N to Z ratio, we have 43 protons and 59 neutrons, and that's going to decrease our N to Z ratio to 1.37. And I wrote down the wrong thing, so you guys probably saw this, but this is actually 1.42. So looking at these nuclides here, can you tell me which one is most likely to undergo beta decay? Again, in beta decay, we see that a neutron gets converted to a proton, and so we're going to use this when our N to Z ratio is too high. What you should have calculated then is that the N to Z ratio for this silicon-22 is equal to 0.57. It's too low, so it's most likely going to undergo electron capture. This rubidium-91 has an N to Z ratio of 1.46. We have 37 for the atomic number and 54 for our number of neutrons. So this is the element that's most likely to undergo beta decay or beta emission. This argon-35, it has an N to Z ratio equal to 0.94. It contains 18 protons and 17 neutrons. So it's relatively stable. You could argue that it's a little bit low, so it might undergo electron capture. And then this cobalt-52 contains 27 protons and 25 neutrons, giving it an N to Z ratio of 0.92. So these last two, again, they're relatively stable. They're close to 1, but they could be increased potentially by electron capture.